Now a presentation on stormwater runoff. How exciting. All right, let's look at where does stormwater go. We've talked about this at depth here, but most of it's absorbed into the ground through vegetation. Some of it's run off, and runoff is going into waterways or streets, in your neighbor's yard. Some of it can be detained in the site, and that was in the presentation you just saw. If it's a detention or retention pond, boom, there it is, or the underground storage, or the wetlands. So for site development, that is including improvements or changes to the site. So again, this is something that you're adding to your notes to a new Google Doc that you've created. And with this, you're going to have some problem solving. So at one point, you're going to want to have a blank piece of paper and a pen and a calculator so that you can do some of these problems along with, and that'll probably be in the very next presentation. So some improvements or changes to the site would be buildings, pavement, landscaping, anything that does not allow water to seep in. Even grading of the site, changing the slope of the land changes how much runoff there is. So typically, development will increase the runoff and decrease the absorption of the stormwater. More water into the streets and waterways, less absorbing into the ground. That's typical. Atypical would be digging up an old parking lot and then planting grass there. Okay, that would actually reduce the runoff, but most things are increasing runoff, decreasing absorption. So regulations have evolved in order to protect the environment, which is water quality. That's a big piece. Sedimentation, you don't want to have erosion where that silt and dirt just kind of gets washed away and fills up the streams, because if it does, then it kind of changes where those waterways go, and that creates all sorts of problems. You also want to protect property by reducing site runoff and reduce impact on storm drainage systems. So if those storm drainage systems get completely over full, then water can't drain into those storm drainage systems anymore, and then you have flooding issues. So some watershed characteristics that affect runoff. There is rainfall intensity. How much rain per hour is generally how that goes, inches per hour. What type of soil you're dealing with, the topography or the slope of the soil, how compact it is. If it's very loose soil, it's going to let in more water. And what kind of vegetation? If you have a lot of grasses and trees, you're going to soak up more water as well. So our goal, what we're going to actually do for our calculations here, and this is going to be part of your assignment, is we want to figure out how we can make post-development runoff equal to pre-development runoff. And in order to do that, we need to figure out what is our change in water runoff from after we develop it. So that's what you're going to solve for, is how much runoff change is there, and that's in cubic feet per second. So you need to calculate the pre-development and calculate the post-development, and these pictures are sort of backwards. I'll talk about those in a second. Then determine what is the change in runoff. How much difference is there that must be retained or detained on site? That's where we have a stormwater management plan. So take a look at these two images. If you start off with an undeveloped area, this is a pre-development, and in Colorado, this would look probably mostly like just grassland, very few trees in pre-developed areas. All the water is going to hit this ground. Not all of it will soak in. Some of it will flow away depending on the slope of the land, but if it's relatively flat, a lot of it will soak in. Now, looking at this from a bird's eye view straight down onto here, we now have this rectangular shaped roof. Another, what I'm going to call rectangular shaped roof, if I look down from the top, all of these are going to be these rectangular shaped roofs. We also have this street that from the top looks kind of like a T if you look sideways at it. And so all of these areas now have increased runoff, and we can calculate that exact amount of increased runoff and then compare that with the runoff that we calculated over here, and then we'll subtract them to find our change. So that's what you're going to need to do. When you problem solve, you have to solve for this one first, you have to solve for this one, then you subtract them. All right, so we do that using the rational method, and here's your formula. So you need to write that down, and now I'm going to define what all of them are. So you're solving for Q, the cubic feet per second of what they call peak runoff rate. So that's how much water is running off of that land. CF is a runoff coefficient adjustment factor, and we'll look at a table. So you just find this value in a table. That's an easy one to get. C is a runoff coefficient, and that depends on the surface, another value you find in a table. I is storm intensity per hour, so we need to look that up based on what type of storm we get. And A, you're going to have to calculate, that's the area in acres. And again, that's in acres So write that down and underline it, or if you're typing this in, most of you are probably typing it, make sure you put it in red, because most times you're going to get how many feet by how many feet, something like that. You have to convert that into acres. So let's look first at CF, and some of you are probably taking screenshots of these, and this one would be a good one to do that with. That's your return period. If it's a 25-year storm, then your CF is 1.1. You plug that in. We had some really hard rainfalls a few years ago, and people called them, I think, 500-year storms. So that CF is beyond this, but it's probably going to be something like a 1.3 or a 1.4. So that's your CF value. I don't know why that was circled there. Okay, there's also intensity. This is depth in inches of rainfall resulting from the storm. That's in duration, in usually minutes or hours during which the rain falls in a single storm. So that value is given in inches per hour. And we'll look that up in a table. Storm magnitude for which the storm water management facilities are designed. This is called the design storm. It's dictated by local regulations. It's described by the return period and the duration. This is a storm that can occur every 25 years, and we assume that it would be a 1-hour storm. That's what that means by return period, a 25-year storm that lasts for 1 hour. So those are two values that you use to find that intensity. Return period is average length. Again, average length of time between the storm. I said 25-year. That was the example I gave. And a 100-year storm has a 1% chance of occurring in any given year. So that's what a 100-year storm is. A 10-year storm has a 10% chance. So we just take, using these values, we can convert that into percentage to get that number. So we look at rainfall intensity, and I have a website that I'm going to have you click on to get that. And it's just a map of the United States. You click on the city that you want, and then you have to choose rainfall intensity. It's a button up at the top. And then down here, it tells you if you have a 60-minute storm, a 1-hour storm, and we have a 25-year return, then it's 1.80 inches per hour. So if you have this full screen, you might actually be able to read that number. It's pretty small. So again, that's found with these charts. And here's a zoomed in version of the Lafayette one. So a 100-year storm that happens for 1 day, 24 hours, is a 5.08 inches per hour intensity. So that is a value that you plug in for I. So here's an example. Suppose a developer purchased a 3-acre farm. Again, we have to convert this into, no, we don't. It's already in acres. Yay! It's in Nashville, Tennessee. That is the pre-developed portion of our data. So right there, we could actually begin solving. We have two problems that we have to do. We have to do the pre-development and we have to do post-development. So pre-development, it's simply 3 acres of farmland. Post-development, it's 30,000 square feet asphalt parking plus whatever is left of farmland. So we need to figure out how many acres this is, and then we also have whatever's left of farmland. So what we're doing is we're developing this by local regulations. It requires it's a 25-year 1-hour rainfall. That's what we have to develop it for, to accommodate for. So we have to find the pre-development versus post-development. So if we use a rational method, this formula, A is the area of the property in acres. This is pre-development. So what you should do is you should draw, this is where you get your piece of paper out. You should draw a rectangle and label it 3 acres and label it pre-development. And we know the area, so we write A. We're going to have to write all these variables down. I, we get the intensity from this website. I'm going to give you that in the assignment. So the intensity for it was a 25-year 1-hour storm, so it's 2.54. So that's our I value. And our C, we get this from a table. So our C value comes from the runoff for farmland. So it gives you a coefficient, and what you do is you look on the table and we say, what is the value for farmland? You're going to see that table in the assignment. And the values for farmland are between 0.05 and 0.3, somewhere around that. So we add them up and we divide by 2 to average them, and we get 0.175. So we can say that's 0.18. So these values are given in a range. Farmland was 0.05 to 0.3. So which number do we choose? Well, that's why it's averaged again. So we get that from this value. That's for farmland. And again, we had to average these. I'm trying to make that as clear as possible. That shouldn't be subtracting there. Adding them to find the average. And then our runoff coefficient adjustment factor, it was a 25-year period, so it's a 1.1. That's CF. So you should be recording all these values down as you're going, and I believe we have all of them at this point. It's 1.0 for 10-year storm. For 25-year storm, which is what we did, it's 1.1. So 1.1 for CF. The C value was 0.175. We said it's 0.18. Our intensity from that table is 254, and the area was 3 acres. So pre-development, we have 1.5 cubic feet per second of water that's running off. That's not the end of this problem, because you have to do pre-development and post-development. So post-development, you still have the same CF. It's still a 25-year storm. You still have the same intensity, but the acreage and your coefficient, runoff coefficients, are going to be slightly different. So 30,000 square feet, if 1 acre is 43,000, it's 0.69 acres. So I have 0.69 acres of asphalt, and the leftover is 2.31 acres of farmland. So now I have to do 2 separate problems. I have to do a runoff coefficient for asphalt, using this as my area, and a runoff coefficient for farmland, using this as my area. So that was that parking. Rainfall intensity is the same, still 2.54. So you found all that information. You just have to plug it in the equation twice, one using this area, one using this area. So let's take a look at that. So still, again, runoff coefficient for farmland is 0.18. We do have to find asphalt. So asphalt in the table that you're going to see is 0.95. It's a really high value because it's very low runoff. So most of that water is getting through. So again, here post-development, you see we have 2 parts of this, 2 equations, or 2 problems that we have to do. We have the farmland piece, and then we have to add the parking. So for farmland, again, CF is 1.1. The C is 1.18, intensity is 254. It's all the same as pre-development. Hopefully you have that written down so you can compare. But the area, now it's not 3 acres, it's 2.31 acres. Because for parking, it was 0.69. Parking is similar to these same values, but the only difference is that C value is 0.95 because that's the asphalt value. So when we solve for both of these, add them up, we get 3 cubic feet per second. So that difference, 3 minus our pre-development of 1.5, is 1.5 cubic feet per second. That's what you actually have to develop for, and this is what I need you to solve for in the assignments that we do. So this is the steps that you're going to go through to solve for these assignments. Again, in stormwater management plan, they use this information to create a water management plan so that release rate does not exceed the peak pre-development runoff rate. So you put in swales or ditches, stormwater pipes, detention ponds, whatever you need to develop in to make sure that that happens. And really quickly, just so I don't leave you hanging, this is the stormwater practice, the link that you're going to click. I've scrolled down a little bit and you see that asphalt had a value of 0.95. We did not average that one. We picked the conservative value, the highest value that's going to give us the most possible runoff on there, just to make sure we allocate for enough. So I'll tell you in the problem if I want you to find the average or the conservative value. Conservative is always going to be the bigger number. And if we looked for farmland, farmland again, remember, was 0.05 to 0.3. That's where we got those numbers, and we averaged those. So in that problem, it was a little ambiguous as to why did they average these and why did they pick the bigger number here. I'll make sure that that's clear when you do your actual assignment. So this is where you're going to find all of those C values. And hopefully that should be what you need to be able to get some of these practice problems done.